I think tonight's event, Tomorrow's Horizons, is a bit of an antidote to all that gloomy stuff we've been reading in the papers and hearing about for the last few years about the state of the world. It's getting hotter, it's getting overcrowded, there are too many of us, too many old people in the West and increasingly in China too. We know these problems. We know that they're a serious challenge to governments and also to the rest of us. But what we don't hear so much about is what is happening in terms of innovation and new ideas and the kind of progressive thinking and inventions that might just give poor old humankind a bit more of a fighting chance and a perhaps less bleak future than we might fear. So how do we challenge the climate and energy gloom mongers? How do we reduce our total carbon emissions? And how do we avoid the basic energy poverty in which huge swathes of the world still live? Indeed, decreasing our own energy consumption along the way. Well, we're going to start tonight with a solution which looks at this, and it is about renewable energy and about a massive solar farming project in Africa. In just 6 hours, the world's deserts receive more energy from the sun than humans can consume in a year. So if only a tiny fraction of this could be harnessed, an area of the Saharan desert the size of about Wales could theoretically power the whole of Europe. Simples. Professor Michael Duran is a physicist at Gießen University and co-founder of the Desertec Foundation. He's flown over specially tonight to explain to us how this might just work and how the desert might be the solution to many of our energy needs. He's going to kick us off with a presentation lasting about a quarter of an hour, then some time for your questions before we move on to the next big idea. Michael, could you join us?
Ladies and gentlemen, thank you very much for the nice introduction by you and for allowing me to speak here in front of this extraordinary audience here. I'm talking about solar farming in Africa, about Desertec, and I have not much time to explain it. So in simple words, it's that you put a solar panel into the desert, you take a long cable up to London, and then you collect your light bulbs here. That is the idea. At the first sight, it doesn't look as a very clever idea, but I have to warn you, we have connections now also to Asia and to South America, and we are infecting more and more people by this idea. And once you have understood the concept, it's very hard to get rid of this infection anymore. That's what I can tell you. So, but being serious, you all know we have an energy problem in the world, and that has two components. The one is that the world population is growing. The second is that the growing energy demand per capita is, especially in these countries where the poverty is now and where the emerging countries are, where we need more energy in the future. If you extrapolate, at the moment we have about 16,000 gigawatt energy demand at any moment. And in the 50 years, we have about 50% more. In addition, we want to get rid of the CO2 emissions to some fraction, and that means that we have to have a lot of new capacities. I put you the numbers in gigawatt, because that is a number where you know what the size means. 1 gigawatt is about the power which one nuclear power plant has. So the energy problem we have is that we need in the next 40 years about 15,000 new 1 gigawatt power plants. So if you would go nuclear, you would need 15,000 new nuclear reactors, which is 1 new reactor every day. So that tells you about the size of the problem, and a lot of us underestimate it. Desertec, we could say, wants to use natural nuclear fusion. You all know the sun is a nuclear reactor. It does fusion every day. At the moment it's down, it's in maintenance, but tomorrow morning it will start again. The sun is highly radioactive. Fortunately, we have a safety distance of 150 billion kilometers, so we are safe here on the Earth. The only thing we still have to build are the solar dishes which collect the energy and convert it to electricity. Now something went off. Okay. I told you how big the energy problem of the mankind if you compare that to the solar power, which is incident on the deserts in the world, you find out, even if you take into account the low efficiencies of these power plants, it's still that more than 20 times more than the energy which mankind needs is available if we would build a lot of power plants in the desert. So in principle, solar energy in desert is capable to solve the energy problem. The question is if this is possible in reality. Fortunately, people have been working on it. Last year, the first solar thermal power plant has been brought into operation in Cairo, in North Africa, in Egypt. And that shows that the technology also really works in the desert. It's nothing which is new. It has been, similar plants have been built in the 70s already in the United States. But this is one of the first ones in North Africa to show that it's also working there. The biggest problem of solar energy is that at night there is no sun. We cannot use the moon to produce electricity. So also here, these solar thermal power plants have a special meaning, a special importance, because they produce heat out of the solar energy, and this heat can be stored in a very cheap and efficient way. Here's an example in Spain. You see the big mirror field where the solar energy is concentrated and liquid is heated up. During the day, this heat is used to heat up another liquid. In this case, it's liquid salt, to 390 degrees of Celsius. You store this hot salt in a second tank here, and at night when the sun goes down, you use this hot salt to produce electricity overnight. So the solar thermal power plants have the big advantage that they can produce power day and night. That is the only advantage compared to photovoltaics, but it's an important advantage. How do we bring the power from Africa to Europe, or from Asia to Japan, or in South America? You can do similar things. When we started these ideas maybe 20 years ago, we were thinking of producing hydrogen and transporting the hydrogen to Europe. Nowadays, with new technology, the things are much simpler. We just put a cable. We have high voltage cables, about 900 kilovolts. And these cables nowadays have the property that they have very low losses when you use direct current. The normal high voltage cables, which you see here in your country, they have AC, alternating current. The new technology uses DC, and the DC power losses are much less, about 10% for 3,000 kilometers. So it's no problem to build a supergrid in Europe where you connect all the countries in Europe, and in addition, you connect it to Africa. That is an example of a second technology. This is a solar thermal power plant which uses a tower. There you see all this mirror field. Each of these mirrors follows the motion of the sun. The light is focused on the center of this tower here, and there you have very high temperatures. You can have very efficient conversion of sunlight into electricity. This is how the things are developed at the moment. In future, there are even more interesting options. In the lab already it works that using these high temperatures together with catalytic reactions, you can produce synthetic fuels with that. For example, a process has been studied in the lab where you use the sunlight plus water plus CO2, and you produce alcohol from it and oxygen. These things work in principle, but at the moment these things are still very inefficient, and it's not possible to do it at industrial scale yet, but maybe in future. Now at the end I want to go to another aspect of desert tech, which is the geopolitical aspect of desert tech. You all know that we have a comparable high standard of living, and there's a large gradient towards North Africa, and that may produce problems in future, in addition, because there's a strong growing population there of young people. Also here, desert tech has an importance. Europe certainly profits from clean electricity from Africa, but maybe even more important, it can profit if we have a secure neighborhood there. And get rid of all these problems which might be there in future with migration and so on. Africa needs energy, but in Africa even more important is water, because at the moment the North African countries in most cases live from fossil water which will be empty in a few 10 or 20 years, and there you need a seawater desalination. Seawater desalination can also be combined with the power from solar power plants, so that you, with the same plant, produce water and electricity. If you do that at large scale, you produce a lot of jobs in Europe and also in North Africa, and you give the young people in North Africa a perspective, so that these young democracies which are arising there at the moment have a chance to be a stable country in future. There have been many people doing these things scientifically in detail. I cannot explain that all at the moment here. The idea is you have certain areas in the desert which are very suitable for solar power plants. You have certain areas in Europe where you have a lot of electricity demand, like London or Paris, and then you just connect these points with DC lines. This is some kind of investment, but we believe, or we calculated, it's always cheaper to build a cable than to build an electricity storage. And by connecting, by having a super grid across Europe, you average out a lot of the fluctuations which wind energy, for example, has, and solar power as well. You can discuss how expensive it will be. The costs are predicted to be something like 8 cents per kilowatt hours for the electricity which comes to London, for example. But of course, there are large uncertainties depending on how fast the degradation of prices is for solar power. Also, the Desertec Foundation has a project together with a company called Tunur, which is a British company and which has some Tunisian investors. They want to do one of the first cables across the Mediterranean to Rome, so that in a few years, if everything goes well, we could have the first electricity from Tunisia. I'm belonging to the Desertec Foundation, but in addition there's this Desertec Industrial Initiative. There are many shareholders. Desertec Foundation is one, and of course Deutsche Bank is one of the important ones. And in the last years there are more and more associated members coming to this big industry initiative. By the way, next week there's a big conference in Berlin where the whole project will be discussed at large scale. And these companies have made a rollout plan a few months ago where they really define how the project could be going on if people want that. The main problems, of course, are political problems. So to finish, Desertec, in our view, solves 4 key problems. It produces renewable and safe energy. It produces water by desalination. It produces a lot of new jobs as well in Europe as in Africa. And at the moment, we are exporting this idea to Asia and to South America. And we believe that here in Europe and Africa, this has peacekeeping incentives, because by this big industrial project, we produce development and economic cooperation between Africa and Europe, and that helps to stabilize the area. Thank you for listening.
Thank you, Michael. I should just say, as part of its commitment to sustainability initiatives, Deutsche Bank is a co-founder and shareholder of DII GmbH, the industry initiative that supports Desertec. I'm going to kick off with a question while you're mulling a really difficult one. It seems to me, coming from a public policy angle, that everything speaks for what you suggest except for the geopolitics and the region and its instability, and the natural concern about the impact of having to pump massive amounts of money and resource into an area which is so unstable. You said that you thought it would be jolly good for Africa, but the Middle East perhaps points in a different direction, that it can be a way these big projects can internationalize existing conflicts and instability. Do you have a quick thought on that?
Well, first of all, we will not start with having 100% energy from Africa. We will start with 15 or 20%. That is the idea until 2050. And if somebody cuts 15% of our electricity, we can switch on again our coal power plants, for example, which we hopefully have switched off at that time, and then we are still safe again. But the real point to me is, first of all, you need, of course, international agreements that the money which you invest is safe in a way. But the European money is only part of it. There are all the Arabian countries which have, in some areas, even more money than the Europeans. Also, the Chinese might be interested to invest in that. And at the moment, the Europeans still have the ideas and are technologically further than the other countries. So I see it as a chance. Now it's a window of opportunity that we invest in that, so that we finally can determine the way how it is operated.
It's a chicken and an egg, isn't it, with stability questions? Because
well,
countries, however good they may find the idea, are unlikely to, they're worried about the impact in terms of their impact on the region as well as what they might get out of it. Best case analysis, great. Worst case analysis, disastrous new James Bond movie. You know?
I like to compare it with the problem we had in Germany with France for like 100 years ago, which were
well, that didn't go so well for a while. You know?
I don't know how it was in Britain. We were really enemies. Yeah, a French person was at least as bad as some people nowadays believe Arabian peoples are. And then we had this Montanunion, I don't know the English word, that with coal and steel you made a cooperation. And by this economic cooperation, the two countries grew together, and finally the European community.
You've got a new 1948 model in your mind.
Yeah. So that is the idea behind it, because if there are political instabilities, we will have problems anyway. So we shouldn't think about how to block that, but how to get rid of this political.
Interesting. Has anyone any responses, questions to that? Please stick a hand in the air. I see one in the second row. If you could just introduce yourself when you ask your question. Thank you.
Simon Tabelem from Realis. One question, you didn't speak about the business aspect of this model, of this new approach, because one of the key motivation normally for this kind of project is who's going to operate it on a business scale. So is it just you're assuming that it's going to be something like philanthropic, or is there any kind of business model?
The Desertec Foundation doesn't want to earn money with it, but the Desertec Industrial Initiative, all these companies are part of it because they want to earn money with it, and they believe the North African market is a big growing market with young people and a growing industry in future. And that, I think, is a motivation for these companies to join the Desertec project. Yeah, there's no company which is there because they think it's a good idea. They just want to get money out of it. And we believe that it's possible, not in the next 10 years, but once it is settled, all the regulations are settled, the international political regulations are there, at some point then it will be a free market model after 2035 or something is what they expect. Until this time, you have to put money in from the governments, basically.
I'd love to take a couple more questions at the back, so I will take them together if I could, Michael, and then maybe you could deal with them together. There were a couple of hands up at the back, I think.
I'm involved in a couple of solar energy projects.
And who you are as well, if it's not a secret.
Gerard Thompson from City and Westminster Corporate Finance. Involved in a couple of solar energy projects, one of which is involved in the desert. And the big problem that, this is the Indian desert, up in Rajasthan. And one of the big problems that we've found is the scarring, or if you will, of the solar panel fascia, and that which limits their life and changes the entire financial dynamics of how these things can do. Do you have any solutions to prevent the scarring of the fascia of these solar panels.
Great, we got that one. Do you mind if we just, because I think we got the idea of that one, I would just like to try and take another question if I could. I think there was one on the other side of the room. Thank you.
Yes, thank you. If I accept your premise on a supergrid...
Could you just give us your name or where you're from?
Tom Sikorsky from Blue Water Energy. If I accept your premise on a supergrid, which is arguably distributing power more efficiently, wouldn't you evolve then to the lowest cost power source across that? And wouldn't that be hydro and nuclear? And how would that compare to this initiative? I would think, just like American gas, it would make renewables pretty quickly.
Yes, maybe I should just shortly try to answer that. The first question was on the degradation of solar panels. The solar thermal power plants, which is one of the technology, is running in the US since the 70s without problems. So they are stable in the desert environment. For the rest, of course, there has to be development going on, and but these technical problems are not the main issues. Yeah, the costs are going down, and the question is how high the quality should be and how long these things should work to be cost effective.
Oh, you say he's got the wrong sort of solar panels. You did say they were scratchy. The gentleman who asked about the degradation of the solar panels, are you just suggesting it's an issue of purely choosing the right things, or that
there is technological research going on to harden the surfaces, for example. Yeah, but these are all technical issues which I don't believe are a showstopper. The other question on the supergrid, I think for the desert tech idea, the main point here is to have the supergrid. That is even more important than to have solar power from deserts. The supergrid allows to have renewable energies with all the fluctuations which are averaged out to some extent. So desert tech not only wants to have solar power from the desert, but also mainly wind energy from the North and Baltic Sea as one of the important ingredients. And if the wind is here in the British area strong, then at the same time in Scandinavia it can be low, and by having this supergrid, these things average out. In addition, if you have wind energy in Morocco, you have the trade winds, which are very stable. Also, that is an important source of energy, which is integrated into this grid. So the supergrid is the first thing. The second thing is then the solar thermal power plants in Africa. At the moment, and you ask about gas and nuclear energy. Of course, you can put nuclear energy into the grid, but that is, of course, not the idea of desert tech. Yeah, we can have a debate on if nuclear power is useful or not. I told you, if you want to get rid of the world energy problem with nuclear energy, you have to build one nuclear reactor every day for 40 years, and alone from the number of engineers you have, it will not be possible to do it this way. That's why we believe you need a technology which is as simple as possible and as safe as possible, because you need these multiple copies of this technology. Yeah, but this is a long debate.
Mike, I'm going to let you off the spot there before you before we have to have the next meeting on nuclear. But thank you very much indeed, yeah. Michael Durham. Right, well, we're now moving on to a different topic, which I'm going to call Waste Not, Want Less. And it deals with our propensity to produce an awful lot of waste that we can't recycle, or at least can't recycle at the moment. And we've all seen those terribly depressing pictures of the plastic islands in the Pacific bobbing along and making one feel very guilty whenever you hurl the orange juice bottle into the bin. But our next presentation is going to be about what might be done about that, and particularly about recycling plastics and extracting the usable energy from plastic waste. Mixed plastic, we know, is notoriously difficult to recycle. Only about 12% of our household plastic waste at the moment can be reprocessed, and the rest is either burnt, which isn't a terribly pleasant way of going about it, or goes to landfill, and you will have seen, if you follow these things, another warning from the Environment Agency about landfill filling up and really not lasting us much longer beyond 2020, unless the hills of England and elsewhere are going to consist of plastic bottles. But a breakthrough does appear to be underway, and here to explain how it might work is Dr. Gary Leake, who is Senior Lecturer at the University of Birmingham at the School of Chemical Engineering and Advisor to Recycling Technologies. Gary, come and join us and save us from all those plastic bottles.
Let's take a drink of water first. Okay, thank you for the kind invitation to talk about my research that I've been doing with a company called Recycling Technologies, basically trying to deal with all the waste plastic that we have around, not just in the UK, but in Europe and in the world. Okay. So how much do we like plastics? Okay. Well, since the 1950s, you can see the increase in the amount of plastics has been used day on day, year on year. And for the people interested, around about 1975, miners' strike, bit of an economic recession, and similarly 2009 you can see the dips when the world consumption of plastic went down, which is a bit of a godsend for us if you're looking from my point of view. We don't want these plastics. Obviously from a business point of view we want them, but from an environmental point of view we don't. So all the plastics that we use generally end up in something that looks like this. This is something you're probably not familiar with, but if you were to take your green bin and shake it across your garden, you may have something that looks like this. So you get a lot of mixed plastics, okay? The problem here is the mixedness of this plastic. So your recycling plant will deal with a certain amount of this plastic. It deals with two types of plastic, so basically your Coke bottle and your water bottle or your milk bottle tend to get recycled and reused into something else. So we're left with lots and lots of other plastic that we don't know what to do with. So where does our plastic come from? Well, it comes from lots and lots of industries, so construction, packaging tend to be one of the largest sectors. And all this equates to 46.4 million tonnes of plastic waste, or plastic that is generated in the EU, and Switzerland and Norway. Okay, so it's E27 countries, and these other two countries. So what happens next? We send 24.7 million tonnes of this plastic to a recycling plant, which is great, okay? You're already seeing there's a bit of a deficit there to start with. Okay, so when it goes to our recycling plant, 14.3 million tonnes of that plastic waste I said that is in your bin, not all of it gets recycled, only 14.3 million tonnes gets recycled of that plastic. Another 10.4 million tonnes disappears somewhere, okay? Goes to landfill. So let's just add up all the maths. We also have another 21.7 million tonnes, the difference between here, okay, that's there. So this equates to basically 69% of plastic that's in the wrong place that we need to do something with. Okay, we've dealt with our recycling here. We can recycle, reuse, turn it into useful products again, or we can turn it into energy. And some countries follow this route more than other countries. So what does this all mean? Okay, so basically we have about 32 million tonnes of plastic waste that we can do something with. If we were to convert this all into energy, okay, if we were to basically crack all the bonds, and I'll come back to that in a minute, what that actually means. If we were to crack all the bonds, we could generate 84 gigawatt hours of electricity, which if you look at the energy consumption for the UK, this would basically power all the energy required for the Greater London and the South East, and more, just from all this waste. Okay? But obviously we need a technology to be able to do this. Taking this a little bit further, just to expand on this, the amount that's recycled, this is 57.9% of the material that gets recycled, so this is 57.9% of the 24 million tonnes that gets into our recycle lines. Let's look at the countries across Europe, and some do it better than others. Okay, so I've highlighted the UK. We tend to follow people rather than set precedents in this area. But we recycle around about 22% of our material, and about 9% we actually burn as a fuel, because it's very high calorific value. Our polymers, we can burn them as a fuel. So we recycle about 31%. So we're below the EU average. Whereas Germany, This is largely from a precedent set from the country. They don't want to put any waste to landfill. Actually recycle similar amounts to the UK, about 30%, but they essentially burn the rest of the fuel. So they burn it in very, very large power plant generation facilities where they usually heat water and raise steam and then put it through a turbine. That in its own right has losses, so you're starting to lose some of the energy that you could potentially use. They're also very, very expensive, and I said, especially in Germany, they have to have support from the government to make these things work, okay? Because the return from investment is very, very low on these, so they usually run at a loss. Problem with these, when you burn the plastics, they also create a lot of heat. So what do you do with the heat? You need to do something with it. So the idea would be to have your great big power plant and to have it next to a housing estate. So the houses could actually use the heat to heat their homes, which they do. But who wants a great big dirty recycling plant in the middle of your housing estate? So we need to think a little bit more smartly how we actually can tackle this. So people can still use these plastics and get the energy from them, but don't have to have all the side effects, all the things we don't want about it. So what we've suggested is a bit of a schematic here, is our system. It's a little bit smaller than these very, very large power generation plants, and they can fit within existing recycling facilities and manufacturing facilities. So basically we have a treatment process, so this is one of our small units, 7,000 tonnes per annum, comes in, we treat it to get it into a particle size that we want, that we can feed into our special unit here. So this is where all the science goes on, so this is the research that I've been doing at Birmingham, is basically making this work. Okay, and I'll come back to that in a minute. The energy that comes out will have, obviously, a calorific value which we can put through a big engine, essentially. We put it through a great big diesel engine, or very similar to a ship engine. Okay. And we can create energy from this. Good thing about this, because they're small, because we can fit them into localized facilities, we don't have to transport lots and lots of plastics to one location site. So we're cutting down on emissions from transportation as well. So let's look at the values. Let's look at the business case around this. We sell these units for about 2.5 million. But if you look at how much you're actually saving, okay, at the moment, because it goes to landfill, a lot of the companies that actually recycle do not want to put these materials into landfill because they have to pay a landfill tax. So a lot of companies are actually storing these materials in warehouses at the moment until the landfill tax or something comes along that can deal with it. So you're going to save between £80 and £100 per tonne, depending on the UK. So if you're processing 7,000 tonnes per annum, you can save £560,000 straight away. Okay? Because you're putting it through an engine and creating 2.7 megawatts of electricity, the end of it, which is enough to power 5,000 homes in the UK typically, you can also sell this electricity to the grid, so you're going to generate just over £1 million in electricity. And because you also produce some heat as well, we can sell the heat obviously to the local facilities, because obviously we'll generate heat. We can sell it to the industrial estate and maybe to some houses, but because it's not this great big dirty power plant, it's a smaller unit, people are generally more acceptable to its use. So you can also save on heating costs about £380,000 a year. So it all stacks up. So over about 15 months, you can get a return on your investment quite quickly. So this all sounds great, doesn't it? You think, great, I want one of these. I'm going to get my checkbook out. So everyone must want one of these, yeah? That is our belief, and probably your belief. So we can build enough machines, we can dot them around the globe, and we can save the world from drowning in this waste plastic that we don't know what to do with, which has a very, very good use. However, I touched on this at the start, this is where the pig's ear comes in. This waste is heterogeneous. It contains lots and lots of different plastics, and these plastics have different calorific values. So if you're trying to produce an output that has a steady calorific value to go into your engine, so your engine runs at a constant rate, it doesn't really happen unless we do something with the technology. Okay, so this is where it all falls down, but we have answers to it. What your energy buyer doesn't want is variability, and this is a big thing that you see with renewables, is the variability in power, keeping a sustained power source all the time. So when the sun doesn't shine, can you store the energy, for example, as we saw? You can. Because your waste also has lots of other chemicals in it, it's not just these polymeric materials, which are, if you think back to your organic chemistry at school, carbon and hydrogen, lots of repeat units make these polymer chains. Okay? But there's lots of other things within them, especially in glues, for example. You get silicons, you get sulfurs, you get chlorines, especially in polyvinyl chloride. So all these have to be treated. So we have a filter section here, because if we let chlorine build up, we can get hydrochloric acid being formed, which will make our reactors fall apart or our system fall apart. But more importantly, things like silicon can react with oxygen in the engine and make sand. You obviously don't want sand in your engine. So there's lots of challenges that we've had to address during this research, and we believe we're at a position now where we can actually go forward with this. So in answer to the question, can you make a silk purse from a pig's ear? We believe you can by some clever technology. And this is just in brief. We have a very dynamic system, so it can react very, very quickly. So our reactor can respond to the demands of our engine. So we get this constant supply of fuel to our engine in terms of its calorific value. So to just talk you through the graph, these are just carbon units. So this is methane, CH4, natural gas, large component of natural gas, and ethane, that we can burn. It has a very high calorific value. Obviously, to crack our long polymer chains down to these units requires a lot of energy. Okay? So what we like to stop at is something where near the green line, about our C6s, so C carbons in a chain. So very similar to benzene, for example, that you find in petrol. So it burns quite nicely. So during our first cracking process, so when we start to break all the chains, if we end up with something on this diagram that centers around C11, to make our process sustainable, so we get in a higher calorific content, rather than going down to the calorific content here about 44, we want it up at 45, so it's constant, we would crack the chains further in the process to get a constant supply of fuel going in to our engine. Okay, so in summary, we believe now we have the technology that we don't have to deal with all this waste plastic anymore. There's the technologies out there that we can find ways to get round storing plastic. It has a high calorific value. It is a very good fuel if the process is there, and we believe it is. And we don't have to spend a vast expense of money to do this anymore. It doesn't have to be located in very, very large buildings. And because of this, it can be applied in lots of industries that have a waste that need to be dealt with. Okay. So I'm just going to throw this question out to you. A lot of governments, especially in the UK, are on about reuse and recycle, i.e. turn something useful, your bottle, into another bottle. They don't always look at the obvious solution, basically turning your bottle into energy. Okay? So we've done some calculations, and we're saying for each kilogram of plastic that's diverted going to landfill, we basically save 1 kilogram of natural gas being burnt. Okay, so we're basically reducing the amount of carbon that people are putting into the atmosphere. This is based on these figures, and if you can see them, so we say that 1 kilogram of plastic has a general calorific value of 31 megajoules per kilogram, so relatively high energy content, similar to coal. And our process works at 65% efficiency, so that's about 20 megajoules of energy, whereas gas has a higher calorific value, but the processes that actually burn gas are very inefficient, down to about 39%, and the comparative figures equate to about 20 megajoules of electricity as well. So this is where my analogy comes from. Okay, so thank you very much for your attention.
Thank you very much, Gary. Now, any questions, and did everyone remember their A-level chemistry? Yes, there's a hand up there.
Of consignment that comes into your plant, how much plastic is recycled and used for something else, and how much is turned into energy, i.e. burnt? Okay, well, when we say it comes into our plant won't exist till 2014. We just take the first order for the first plant. So our aim would be to try and get hold of all that waste material that is going to go to landfill. We wouldn't touch the material that already has a current use economically
that can be then reused or re-engineered into another milk bottle or another Coca-Cola bottle, so we wouldn't touch that. So we'll be aiming for this 69% of material. In the UK, obviously that was across Europe. In the UK, it's about nearly 2.5 million tonnes of plastic waste that we can get our hands onto.
Anything else there? Yes, I can see a hand at the back, right under those very nice bright lights. I can't actually see who's on the hand.
Thanks very much. It's Chris Hocking from Deutsche Bank. I'm just trying to work out, if dealing with all the different types of plastics coming into the unit is so difficult, why not speak with Coca-Cola and get them to make all their bottles out of the same material?
They're made out of that material because it has a certain quality that they're looking for. They're looking for opaqueness in their bottles, whereas milk producers have always gone down the route that you don't have to see your milk. So they're doing it from a marketing point that people want to see their drink. And I'm doing a lot of research into biodegradable cling film. The problem with cling film at the moment is not biodegradable, but trying to make that biodegradable is very, very difficult because it has very unique properties. And what all we end up with all the time is something that's quite opaque. So you take it to the consumer and they want to, so when you buy your pack of tomatoes, you don't want this cloudy opaqueness on your tomatoes. You want to be able to see your product. So this is the challenge that we're faced of. It's the public perception of what a product should look like on the shelf. And if you change that, they will go somewhere else. They'll go to another competitor. So I think we're stuck with how Coca-Cola want to market their products.
And are the key manufacturers, are they sympathetic, empathetic to wanting to close that loop? Or is it truly the consumer that's driving that agenda?
No, you'll find that supermarkets have agendas for their suppliers. Their suppliers need to tick green boxes essentially. So if you have a supplier that doesn't have certain legislations in place or acts to act environmentally in how they produce their goods, then they can essentially go elsewhere to find another supplier that does tick this box. So suppliers to supermarkets now are very, very sort of keen to actually tick these boxes. So they can go back and say all the energy that's been used, all the materials that's been used in a process or in a product actually gets used for something at the end rather than just lying stagnant in a warehouse or in the ground. Okay.
Gary, could I just follow up a sort of point from the first question, really, which is whether, in a clever way, you don't solve one environmental problem and create another. And I'm thinking particularly about natural gas and the fact that it is captured when you make the bottles as a feedstock. And then, of course, you're proposing that you would release some of it back into the atmosphere, which has been one of the big concerns that we've been trying to address. I suppose it's the equivalent of robbing Peter to pay Paul.
That is true. You will produce some emissions from the process, but with the carbon capture that's available these days, if you look at the power generation plants for coal-fired power generation, are much less polluting than they ever were because of carbon capture facilities. And these plants do have the current.
And you're sure that the margin of capture then makes up for the, well, basically what you're releasing compared to what you're saving?
You've got, I suppose it's one of those things if you don't do anything with it, it's still going to be there. And there's a lot of energy gone into the processing of that plastic in the first place. So you might as well do something with it. And rather than burn natural gas, this is my point on the last one, rather than take a new source of natural gas from the North Sea or from Russia, we can actually burn these plastics to provide the same amount of energy.
Yes, there's another question. Thank you. There's another question at the front. So.
Nigel Kershaw, CEO of Big Issue Invest. I'd love to invest in it, but
he won't stop you.
I know what I'd do, because I think any of the profit we'd make, I would like to put back in actually going upstream and solving the problem why it exists in the first place. Because I think, although I think you have to do something like this, actually what we have to do is start changing how we produce, how we consume, and the rest of it. And now if you look at the convergence between environmental and social, and you've only got to look at a famine or water or whatever, unless we start to do that. So I think as a short-term solution, absolutely yes.
Yes.
As a long-term solution, we really have to get our energies into manufacturing and how we consume if we're going to go and essentially invest in this to put ourselves out of business.
Yeah, I totally agree with you. It's a short-term interim, probably a 10-year plan, hopefully. I mean, if you saw the first figure, where the use of plastics over the last 50 years has been increasing year on year on year. We need to do something with that so we reuse more of that plastic. I mean, everyone at Hope, there's figures on mobile phones. People around the world have 3.5 mobile phones in their drawers somewhere, okay? Which is a lot of plastic and a lot of rare earth metals that need to be reused. So still we start thinking about how we tackle these problems. The problem is we make things too complex to basically reverse engineer to actually take back to pure components, and they're a lot easier to process. But when we have this mixed plastic waste, I think this at the moment is the only alternative that we can go.
Anyone absolutely burning to do another one, or should we let Gary off the hook? Thank you very much.
Okay. Thank you.
Right, well, there's no other way of saying this. We're just about to learn about a project that aims to turn poop into power with a toilet or lavatory, depending on how strictly you were brought up, that transforms human waste into charcoal, salt, and clean water without the need for electricity. It really does sound too good to be true. The Gates Foundation is funding a project, and here to tell us about it and how it would work is Mohammed Sahel, who is Professor of Sustainable Infrastructure at Loughborough University. Sahel, could you step up here? Thank you very much.
Good evening, ladies and gentlemen. Today I'll be talking about toilets. I have, in my previous career, have managed pretty large construction projects, airport terminals and constructions, but I'm finding this project one of the most exciting. So I'm going to just take the liberty of sharing some of those ideas with you. I'm sure most of you would know Mr. Gates. Besides one of the richest person on earth at the moment, he's one of the very active philanthropists. I didn't realize that the money that he's putting in the foundation is basically his personal money, and it has nothing to do with the Microsoft Corporation. So the foundation is going on for some time, and I think they have a portfolio of $4 billion at the moment, including lots of vaccine preparation, agriculture, and one of the programs is water sanitation and health hygiene. There are two main components of that. One is basically supporting our conventional water and sanitation with the view to increase the access to safe water and safe sanitation. But they have also come up with another stream of program which try to really shake the whole sector by challenging the experts to come up with new ideas. I think there is a realization that many of these ideas may not work, but there is a reasonable chance that some of those could turn into either individually or in combination game changers in the sector. So that happened on 14th of August this year, when after our first phase, we were asked to go and present our prototype in Seattle in front of the panels. And I was given, in the end, 5 to 6 minutes, and I was constrained to do 3 slides in front of Mr. Gates. And after that, we were given the second prize on our concept. We were beaten by Caltech, but we sort of were ahead of Stanford and some other universities.
You noticed.
So basically, if you look at these pictures, what we have proposed is to convert just these. This is basically fecal sludge, or basically shit, which is very hazardous and harmful. And through the process, we are trying to convert that into valuable material safe to touch. And these are the real pictures, and I forgot to bring some samples because it smells like coffee. Apologies to coffee lovers or caramel, and you can feel the granules of that. So basically, what we are trying to do is to, before I go on that, let me give the bigger picture. 3.2 billion people at the moment don't have toilets. The people who have toilets, you don't really know where the excreta is going, whether it's treated or not. Even in Europe, there are cities where human excreta is more or less dumped straight into fresh waters, and there's a whole implication of that. So it is not just the developing countries issue, and if you think about health cost and things, diarrhea, there's thousands of children are dying every minute as we speak because of lack of toilets. So basically, we want to have toilet, which basically is desirable. So if you go to many countries, you don't want to use loo because they are so dirty, they're smelly, and it's very hard to go in. So I think in our team, we have people from design school, from chemical engineering, from civil engineering, and from materials working together to create a desirable space in toilet so that you can also treat your toilets respectfully. Now, why we are doing that? Because I think studies have shown, World Bank, I think, that we have the least willingness to pay for our toilets or sanitation as compared to highest willingness to pay, let's say, for power and telecommunication. And that creates lots of problem for developing any business case for investment. We think, along with just treating the normal fecal sludge, we will be exploring whether menstrual hygiene waste could also be treated, because that is one of the things which we don't talk about, but there are many countries where there's a huge loss of students when they reach to that stage because you don't have toilets to deal with that menstrual hygiene waste. So we are thinking about whether some of the technologies we are going to develop could also treat organic aspects of that waste. Then we have a market, besides the developing countries, even in states and here, where you don't really have piped or network connections. You have big gatherings. I was told that this year, Glastonbury festival was postponed, and one of the reasons was that they didn't have the toilets because all toilets were moved to Olympic. I don't know, but there are lots of big gatherings where you do need standalone mobile toilets, and you don't have the real connection into the system. So what we want to do is something which is desirable for users, self-cleaning. So we don't want to use quite a lot of water, because at the moment, if you think about that, if I remember correctly, the figure is like half a kilogram of excreta that we produce, an adult produced in many societies, and then we use for each flush like 5 liters of water, and we use all of that thing and we transport it miles and miles, and then we treat using lots of energy and lots of space. So apparently common sense tells you that maybe it's not that smart to transport the whole thing and then you treat it in a very resource intensive way. So we want to make it smart. The challenge is to make it easy to maintain. So we are experimenting with some sort of nano coating, which basically will reduce the stickiness of material with that. Cultural acceptability. The world can be divided into people who sit and people who squat, people who wash and people who wipe, and there are associated difficulties with what you design. I've come across some people, using material and then trying to flush. And in one case, I saw people using, rocks in some hilly areas and trying to just flush it. And we were given this remit that it should be non-piped solution. And it has to have least dependency on energy sources. So before I go on that. So what we did was basically, the principle is very simple. There are some discussion about energy. There is a very good link between what we eat and what we excrete. So when you eat, you have some calorific value on food. 2,000 calories we eat. The thing is, what comes out, it still has some energy. And the figures people show using different diets is from 5 to 20 megajoules per dry mass. So the idea is that whether we can recover some of that energy from something which we try to just treat and not use. So that is one. The process that we are trying to use is called hydrothermal carbonization, which basically occurs naturally in converting material into, like sludge into coal. But that happens over millions of years. So what we are trying to do is to achieve that in a very short period of time. And again, very simply, it is basically sort of pressure cooker, where basically you try to get the heat up to 200 degrees centigrade under 20 bar pressure, which basically kills almost any sort of known germs and things, and convert the material. And what comes out of it, basically 3 streams of things: some solid suspension, which we could extract and use for combustion, or we can use for soil improver. Liquid stream, we could extract some materials, nitrates, and gas, which we are thinking of looping back into the system. So very simple principle, linkages between the energy we take in and what we can recover, natural process, and then trying to use that as much as possible to run on its own. This is not a toilet, if you are visualizing where the toilet will go, but just a prototype to show our sort of concept. So if you think about, and if you want to visualize that you may have toilet somewhere there, and the waste is collected in this collector, very simply. Then we have a pump. Now, we are using pump at the moment, but that could be replaced by a solar-powered or some sort of, this is like, it uses, I think, 1.5, a lot less energy. So basically, the real thing which is happening is in this reactor, which again, to show the process, we have used the off-the-shelf components. This is basically a heat exchanger. It has 3 tubes inside, so material goes and passes through in 3 loops, and by the time it reached there, it has attained the temperature. Then basically material goes up, we sort of like reduce the pressure, and then the liquids and gas are collected. Basically, this prototype, basically could be used by 100 users. Now, because our phase 1, which was basically to prove our concept, was to do exactly that, because what is needed is ultimately to have household toilets which are using new principles. So that is the prototype which we took to Seattle. It doesn't look like toilet, but it shows the principle. Now, what I'm going to do before we go to question and answer thing is to recap that in May-June 2011, Gates Foundation invited 25 universities. They selected 8 universities, including our university, to come up with ideas, and then they gave this prize to 3 universities, Caltech, ourselves, and Toronto. Different technologies are being proposed. And recently we have got funding for the phase 2. And the challenge now is to develop this concept into technology readiness level 7, which basically is lab-tested system operating in operational environment. And we all are very excited to work towards that. We haven't finally resolved all the issues, but we think that we are on roads to some game-changing technologies. Thank you.
Thank you, Sahel. Now, who would like to ask a question on reinventing the humble loo? Yes. A fellow panellist, no less.
Hi, Gary Leet, University of Birmingham. How do you deal with changes in pH? I mean, say someone's sick in the toilet. Won't that change the bacteria flora?
You see, our sort of, the thing is, at 140 degrees centigrades and above, we think all sorts of germs will be burned. So in terms of dealing with pH and things, of course, and of course the big issue is that if, let's say, all of a sudden you have a party in a house and there's lots of beer, and then all of a sudden your proportion of solid becomes like less than 8%, because the idea is that you need to have certain amount of solids to produce the energy. So if your proportion become less than 8%, almost liquid, then what do you do with that? These are the kinds of questions that we are sort of considering. But there are some large plants already operating, HTC, dealing with solid waste, particularly in Germany and Switzerland, where they are using 25 to 30% of proportion. But I think these are the kinds of things we'll be looking at. And especially the big challenge is how we can reduce the scale, because we need a household toilet, but then in household we may not have the energy, the mass to generate the energy. So we may have to compromise a bit, and we may think about, like, rather than having just 20 users, we say, look, the minimum would be from 30 to 100 or above.
Yes, thank you to Gary for raising the Saturday night clubbing objection to that one. And anyone else got a question? I think you've wowed them all into silence with the reinvention. I mean, I just have a practical one which may have crossed people's minds, which is simply cost. I mean, you alluded to it there, that you might have to sort of upscale to start with. I mean, even simpler new loo technologies. I got carried away with a Clerkenwell architect recently and almost agreed to having something where you washed your hands and then you used the wastewater for the toilet, which then turned out to cost £2,500. It's just... So, I mean, have you thought about how quickly you could get cost to a level that was scalable?
The target that's set is like 0.05 or 5 cents per user per day. Is the target that we are aiming, like $60 per family per month.
But my point is, if it's already so expensive, even to do something which sounds a bit simpler, which is to use wastewater, then
the thing is,
what's the timescale?
What maybe you're not adding in, that is not just that cost, but maybe £20,000 per family that we sort of incur in the UK for the pipes and everything. That's not really counted. So the thing is that our existing system is really very expensive. So I think you have a point, and it all depends on the standards as well. So I think our design team, along with the other grantees, will be looking into, because I think we do want to have like market segmentation. So we can think of like people who can spend lots of money on that, and also people who are poorest of the poor in developing countries to afford. But that's the target that we are aiming to.
Fascinating. Thank you very much. Thank you, Zahab. Right, then, well, stick with us, because for our last slot tonight, we're going to be looking at how new technology can be applied to our cities, make them smarter and greener without sacrificing their essential character and respecting their history and the traces in the present. So please welcome Steve Rayner. He's James Martin Professor of Science and Civilization at the University of Oxford, who's going to be talking to us about flexible cities. Steve, come on up.
Thank you, and thank you for the opportunity to come and talk to you a little bit about the Oxford programme for the future of cities. I'm not going to be talking about a specific technology tonight, but I'm going to be talking about a context in which technological change over the next 50 years is undoubtedly going to be extremely important. And despite rejoicing in that wonderful title of being Professor of Science and Civilization, I'm severely E-challenged, and this may end up going backwards rather than forwards. No, I'm in luck tonight. One of the foci of the programme for the future of cities at Oxford is mundane technologies and infrastructure change. And it's only that particular one that I'm going to talk about this evening. And I will get round to talking about toilets in a minute, taking up Professor Sohail's theme. But before I talk about toilets, I want to talk about typewriters. I'm sure that most of you will recognize that sequence of letters on the top of this slide, right? It is, of course, the top line of the standard English typewriter keyboard. Does anybody know why that's the top line of the standard typewriter keyboard? Yes, madam?
To make you type as slow as possible because the keys couldn't move fast enough.
It was in the days when typewriters were first invented, the keys would jam. And it was, in fact, designed to slow typists down. Some people think it was designed to actually speed people up, but it was actually the opposite. It was to slow typists down because the keys were jamming. Now, when I became a junior researcher at the Oak Ridge National Lab in Tennessee in the mid-1980s, I had one of these things on my desk when I first went in, an IBM golf ball typewriter, no keys already, still had the QWERTY UEOP keyboard. A couple of years later, we got up to date, and I had one of these things, one of Mr. Gates's Apple II computers installed in my office, and not even any printing device there. So why on earth are we still using this sequence on our keyboard? And the answer is, of course, that when we talk about technologies, we're not just talking about gadgets and gizmos, devices. We're talking about the way pieces of equipment are embedded in social systems and in systems of use. And of course, it's things like touch typewriting courses and secretarial schools and things of that sort that have embedded this technology, even though the reason why we had it in the first place has gone away a very long time ago. And I now want to move from typewriters to the city. Because, of course, this phenomenon, what we call socio-technical lock-in, is very familiar to us in terms of our urban morphology. The road plans, the street plans of many of Europe's major cities were laid down in Roman times. Some of you will recognize straight away, this is, of course, the schematic representation of the City of London. You can see the outline of the old Roman wall, the old Roman street grid plan there, which has persisted now at least 1,500 years since the Romans left Britain in the layout of the City of London today. But I want to emphasize that this lock-in isn't just physical, it's also ideational. This is an artist's representation of the archaeological remains of Ur of the Chaldees, which was the city from which Abraham got up and left to invent monotheism. And you can see here, of course, the classic morphology of the city, the ceremonial center of political and economic power and religious power, spiritual power in the middle here with the ziggurat and the pyramid, the royal palaces around it, and then you see the commercial and residential areas around that and the port off into the distance. You can fast forward about 4,000 years, and this is, of course, Abu Dhabi today. And one is tempted to suggest that although the god has changed in 4,000 years from whoever they worshipped in Ur before Abraham to Mammon, this sort of central morphological concept of the city with the big monumental works in the middle still remains very much something that we think of when we construct cities. So the question is, how do we think about this question of lock-in? Is it all bad? No, of course, because actually it's also, in a sense, the lock-in to particular ways of doing things that gives cities their particular character and make them places that people want to live. And they want to live in London rather than some other place precisely because of lots of the things that have persisted and become embodied in the material structure and the fabric of the city. But on the other hand, we also recognize the need for change. Change in our energy system, change in the way we process human waste, our use of fresh water, and so on. And I just want to emphasize that what I said earlier, that technologies are social systems mediated by materials and devices. We shouldn't think of them just as bits of kit. This is a frequent mistake, and there is often a dichotomy drawn, which I think is quite false, between bringing about behavioral change in order to promote sustainable development and bringing about technological change. You don't change kit without changing behavior. If you start to want to introduce a different set of technologies, you need to train people to actually be able to install those technologies, as you mentioned, with respect to the very high costs of the grey water system that you were looking at in your own home. You need to train people to be able to install those, maintain them, so on and so forth, know how to use them. Similarly, if you want to change behavior, you need when you want to get, for example, more people using public transport, then you have to actually change the kinds of public transport and the way it operates that you're making available to them. So they are really inseparable, these ideas of behavior and equipment. And the other thing that I want to emphasize is to suggest thinking about the city as itself as a technology in this sense, and not just as a single technology, but a nest of technologies. And I'm going to dig down now into that nest and talk about a few of them and the way that they've shaped the city and some thoughts about what the prospects are for change. And of course, this was a very early shaper of the city as we experience it. It's the sailing ship. For millennia, this was the only serious way of moving large, heavy cargoes around the planet. And as a result of that, 23 of the 30 largest cities in the world are built on the coast. And much of the infrastructure of those cities that are built on the coast is either at sea level or it's actually being built on reclaimed land, which is at or below sea level. And that, of course, makes them particularly vulnerable to problems of climatic variability. This is seeming rather dated given today's news. This is actually a scene of the Crescent City, New Orleans, after Hurricane Katrina. Now, I'm sure that Hurricane Sandy will reignite a lot of the debate about whether or not we've had an increase in hurricane intensity and frequency as a result of climate change. As I understand the science, actually there's been a very slight increase in hurricane activity over the last 50 years, but if you go back over 100 years, that trend disappears. And we shouldn't forget that the worst hurricane the US has experienced, at least to date, historically was the Galveston hurricane in the early 20th century. But what actually led to this scenario wasn't increased intensity of storm activity. It was a failure of the technologies which have been put in place to actually protect New Orleans from flooding. It was a failure of the levees system that was in place to do that. And although I said that the cost of, that the intensity of hurricanes probably hasn't increased much over the last 100 years, the costs of hurricane damage over the last 50 years from wind and water damage have soared exponentially. They've really gone through the roof. And the reason is actually asset location. Anybody know where this is? It's Miami Beach today, okay? That's Miami Beach today. That's Miami Beach in 1920, okay? Miami Beach today, Miami Beach 1920. What's causing the costs of wind and water damage to go up? It's clearly putting expensive infrastructure, fragile infrastructure in silly places like low-lying barrier islands. And there's an awful lot that can be done with just simple, straightforward things like the adjustment of building codes and the enforcement of building codes. For those of you who remember Hurricane Andrew a few years ago in the US, there was one builder in Homestead, Florida that didn't lose a single roof in Hurricane Andrew. And I'll wager you all know the name of that builder. Anybody want to hazard a guess? It was Habitat for Humanity, the self-build charity that Jimmy Carter heads up for helping poor people to build their own homes. When asked what their secret was, they said, "We don't know, we just built a code." Wealthy countries can protect dense populations through hard shell protection, through building coastal defences like the Thames Barrier. And of course, if you're a wealthy country, you can do this across the Thames, you can do this across the mouths of rivers and places and so on. That's not really an option that's available for people who live on the Sundarbans in the Ganges Delta. It's not available for more diffuse populations, as you can see here. Bangladesh, by the way, is a country that imports rubble. It imports other people's demolished buildings because of the lack of stone for basic construction purposes. So building hard shell kinds of sea defences is really not on the agenda for them. But we can learn from the poor, actually. These pictures here are of a place in Cambodia, the Tonle Sap Lake. Some of you who may have noted recently the passing of former King Sihanouk. One of the roles of the of the Cambodian king is to preside over a special ceremony which happens when the Tonle Sap River reverses its flow, as it does every year. It's the only river in the world that does this. It's a tributary of the Mekong. And in the monsoon season, the water flows into the Tonle Sap Lake from the Mekong, and as it dries out, it flows out of the lake into the Mekong downstream. This means that the actual lake edge fluctuates by many kilometers over the course of a year. This presents you with a particular problem if you are deriving your living from the lake. A lot of people deriving their livings from fisheries, particularly. If you build your home at the lake's edge in the dry season, you're going to have real problems in the wet season. And if you build it on the edge of the lake in the wet season, you're going to have an awful long walk to work during the dry season. Added to which these people are actually too poor to buy land anyway. So their solution was to build villages actually on the lake. And you can see here there's the floating church, they have floating grocery stores, cinemas, so on and so forth. And this is not just unique to Tonle Sap. Actually, you find these kinds of floating villages also in Vietnam. There's one in Hong Kong Harbour, actually in the Far East also. These ideas are now being taken up using modern materials and design techniques, in this case by Dutch architects. And we usually think of the Dutch as being the kind of the masters of the hard sea defence approach to things with their history of constructing dikes and seawalls. The top picture is actually a house in a village in the Netherlands, which is floating and can move up and down about 3 meters with fluctuations in water level. The lower picture there is an architect engineer's impression of an apartment building. It could be an office complex that could be built that was floating on the water. So thinking about perhaps how do we take modern materials, modern design techniques, and take traditional ideas and transpose them into ways of adapting to deal with the challenges of sustainability. Professor Suhail has already spoken at some length about the challenge of the toilet. It's also a pet topic of mine. Nobody in their right minds, as Professor Suhail has already said, would have deliberately designed a system whereby we purify billions of gallons of water to drinking quality to flush toilets with. This is absolutely nuts. And indeed, nobody did design that system. It came about by accident. It came about when various engineers started putting sewers underground because of problems like the Great Stinks in Paris and London in the 1850s, problems to do with contaminated drinking supply, such as cholera and the famous, this is the Broad Street pump. You can go visit it up the road here in London, where John Snow famously removed the handle of the pump in order to prevent people from drawing water from it because of cholera contamination. And it was really the combination, simultaneous combination of people putting sewers underground and piping in fresh drinking water into the newly emerging industrial cities of the 19th century that were then linked together, almost incidentally, by Thomas Crapper's improvements to the flushing toilet. The flushing toilet had actually been around since the 16th century, but he did the siphon-operated technology here, and linked those two previously separated systems together. Now, Professor Suhail has already explained part of the motivation for moving away from this technology, which is actually trying to help poor people in developing countries to have adequate access to sanitation without committing themselves to this unsustainable way of linking drinking water supply and human waste management. But the interesting thing, I think, for us at the moment is that this impetus also coincides with two other opportunities. One is the increasing amount of construction in semi-arid areas. This is Orange County in the United States, where there actually is a strong incentive for grey water systems and other ways of saving water and perhaps moving away from this piped infrastructure. And of course, we also are all familiar with this kind of picture at the top right there, as you look at it, as we find the existing water infrastructures of our cities decaying. So for once, perhaps, the interests of the wealthy and the poor in the world can be brought to coincide in the development of precisely the kinds of technologies Professor Suhail was talking about. Interestingly enough, in the same year that Thomas Crapper patented his siphon-operated flushing lavatory improvements, the Reverend Henry Mole came up with the Mole's Earth Closet. Had that technology taken off, we might today be going for a mole instead of going for a crap. But the point is that there are now increasing interest in the kinds of technology that Professor Sohail talked about, but also other kinds of alternative pipeless technologies involving composting and so on and so forth. Another technology I'll just briefly touch on that's done much to shape the city in the last 50 years. This is the lovely Lutyens building, which is the British Embassy in Washington, D.C., where diplomats until 1945 got hardship pay. I lived in Washington, D.C. for 10 years, and I can understand why. It really sucks in the summertime. They stopped getting hardship pay in 1945. You know why? The air conditioner. And by putting the air conditioner in, basically the need for hardship pay went away. Now, it's very interesting that the early manufacturers of air conditioners actually wanted to standardize production. Prior to the air conditioner, it was widely recognized that people, different sorts of people living in different parts of the world, had widely different tolerances of heat and humidity. But by standardizing and naturalizing our requirements for a particular temperature and humidity, the air conditioning industry was able to streamline mass production for air conditioning, and we saw the transformation of sleepy southern cities like Atlanta into the vast metropolises that they are today. And we also saw at the same time a standardization of building design around the world, where we no longer had to take account of the natural conditions and adapt to them, which has actually exacerbated the urban heat island effect, which actually then requires more air conditioning, more electricity, more greenhouse gases, so on and so forth. Now, it's interesting that once again we are beginning to see architects and engineers taking traditional designs and ideas and using modern materials and design techniques to bring them up to date. So this illustration here is the Queenslander house. This was a typical Eastern Australian house, funnily enough, in Queensland. And you can see it has many distinctive characteristics: the 360-degree air circulation, the wide eaves over the balconies, and so on, making the most of natural cooling. What happened when air conditioning came along, by the way, was a lot of people filled in the bottoms and made them regular two-story houses. They were sorry when Queensland flooded later, but anyway. We're now beginning to see, though, architects and engineers taking those design principles, and you can see this building below, which is on the Okanagan campus of the University of British Columbia, where the 360-degree air circulation through an elevated roof is used to provide similar natural cooling to the building. Another example is this one here. This is the wind tower. You find these all over the Middle East, from Morocco to the Yemen. Traditionally, the wind blowing across the rooftops was ducted down into the buildings below to provide cooling. And Norman Foster, in his Masdar project, has adapted that. He got aeronautical designers to design this kind of a structure here, using the most up-to-date computerized technologies for designing aircraft wings and so on, to get the most effective conductance of cooler air down into the square below, and indeed on a massive scale, taking air down into the rocks below to benefit from natural cooling. I couldn't talk about technology shaping the city without briefly at least touching on the motor car. In 1896, the Red Flag Act was repealed. This was the act that required in England that any motor vehicle, horseless carriage, had to be preceded by a man carrying a red flag. Incidentally, in the same year, 1896, was the first pedestrian traffic fatality in the history of the world. It happened not far from here in Croydon. A young woman going back from a day's trip out to the Crystal Palace was run over by a French demonstrator model. The Croydon coroner said, and I quote, "This must never be allowed to happen again." Go figure.
Steve, are you able to conclude in a minute or
Just
so?
a minute, literally a minute.
It would be lovely.
In less than 60 years, in less than 100 years, certainly in the US in less than 60 years, we went from the Red Flag Act to this kind of configuration. Now, in some ways, that's frightening, but in other ways, it might be an opportunity for a little bit of optimism as well, because it shows that when things are aligned in particular ways, you can actually have very rapid technological change and very rapid infrastructure change. Traffic in London in 1900 went at about 11 miles an hour. Traffic in London in 2000 went at about 11 miles an hour. And another possibility here is we've all heard of the Boris bike. Is the equivalent might be the sort of Boris car, or whoever it is that comes up, not the Boris Karloff, But anyway, the idea here is basically you've got driverless vehicles that are moving around the city with computer-controlled routes. You would then get out your mobile device and simply say, I want 3 people going to such and such at such a time. The computer would then calculate the deviation from the existing route for one of these things to come and pick you up and take you in relative comfort to where you're going. You don't have to park your car. You can have a few glasses of wine and not worry about getting breathalyzed on the way home. Isn't that a marvelous idea? So there's ways in which here we can see, in a sense, a return almost to the Victorian notion of the cab and the hackney carriage, traditional ideas. I don't have time to talk about the light bulb or about the elevator. But certainly without those innovations which happened in the 1880s and the 1850s, respectively, we would never have seen that. And I would say without the flush toilet as well, actually, and the light bulb and the elevator, we would never have seen that. After today, we may not see that again, but I sincerely hope that won't turn out to be the case. Just to briefly mention transitional technologies, it's important that we understand technologies that take us from where we are to where we could be. This one's very important, the oil lamp. Humanity's only ever given up one energy source in its history. Anybody know what it was? Whale oil, exactly. And why? Because you could burn kerosene in the same lamp. So it took you, it was a technology that could take you from one technological configuration to another. Same thing with hybrid cars. I will predict they won't be around in 15 years' time. We only really have the gasoline engine in there because of people's range anxiety. I could tell a similar story with respect to air conditioning and so forth. Finally, greening of buildings. Actually growing ivy up the walls of buildings to provide cooling and insulation is a very old practice. We do it a lot in Oxford. This is actually a building in Singapore, and there are people who are now thinking about the possibility of pushing that idea even further into vertical horticulture, vertical agriculture. I don't think we'll ever feed the world this way, but it certainly could change the way that we're living in cities. So I'll just finally leave you with this image. This is by the Argentinian artist who works in Frankfurt, Germany, Thomas Saraceno. This is an installation that he did in Hong Kong, Cities in the Sky. Not, again, because I'm suggesting that we'll be going there anywhere soon, but it does, I think, bring home that thinking about the challenge of sustainability in urban environments isn't just a design problem or a manufacturing problem. It really is a challenge to the human imagination.
Thank you very much. What an amazing world tour you took us on in your allotted time. Thank you so much. I should also point out, one of the few things not in your slides there was that Deutsche Bank has created one of the most eco-friendly high-rise buildings in the world when it refurbished its Frankfurt headquarters not so long ago. So 98% of its pre-existing space was recycled, and the result is an 89% reduction in CO2 emissions. I knew all this before I came. And a 74% reduction in water use per year. So beat that or go and have a look at it. Running out of time, but I wonder if we could just, if any questions that arise from that fantastic panoply of things that Steve brought up, perhaps we could take a couple together. You cannot have lost the will to live after that. It was so stimulating.
The will to drink is stronger.
I think the will to drink may be stronger. And you were the one who brought up the wine. Now, look, now, but someone has resisted. Yes, sir.
I'd be interested in knowing why you think the hybrid car concept or production of hybrid cars won't be around in 15 years' time.
Yes. Well, because largely the hybrid car is a transitional technology. It's the one that enables us to still have mobility and to be able to rely on gas stations or petrol stations in order to fill the cars up to ensure that we have an adequate long-distance range. On the other hand, we want to have the benefits of an electric car. As plug-in electric vehicles improve and people have more confidence in their range and also realize that actually most of the time they don't drive that far, that they're going to run out of battery juice. And as batteries improve, as all those things happen, the need for keeping that vestigial gasoline-powered engine in the vehicle will go away for most car uses. Certainly those that are uses within the city or within the urban environment. For other uses going between cities, that's a different, maybe a different situation, and it may well be that we will rely on things like hydrogen fuel cell vehicles for those longer distance transportation. Certainly, we may well be looking at hydrogen fuel cell trucks and buses in the future. But again, I think we will be moving away from the gasoline engine.
Yes, Tony.
You can come and find me in 10 years' time, 15 years' time, and tell me if I'm wrong.
So
you're coming a hybrid car.
So Tony Curzon-Price from Intelligence Squared and Open Democracy. You put a lot of emphasis on lock-in, but I wonder about emphasis on the opposite thing, which is surely at a suitable historical scale, every technology is transitional, and doesn't that apply to the city as well? And what are the developments which would actually make the city obsolete? And aren't we seeing one of them, which is very good non-atom-based transport and communication through transport of information?
Just to the contrary, I would argue, in fact, that far from the city becoming redundant or outliving its usefulness, we are living in the middle of the biggest migration in human history. The biggest migration in human history. Over half the world now lives in cities. It's the migration from the countryside to the city. Within 20 years, it'll be 70% of the world's population living in cities. And I think that's terribly exciting because there's all sorts of things you can do when you've got a concentrated population. You have much more creativity, which you don't actually get with the extended networks where you don't have face-to-face interaction that you get with the web. That serves a different purpose, and it can reinforce that face-to-face interaction, but it's terribly important. If you look at any of the works of people like Richard Florida and other authors who've been looking at the way in which cities are centres of creativity, they will all emphasise that it's the density of population, the serendipitous interchanges that people have, meeting with each other, bringing ideas together and so on, that seems to make a city flexible and dynamic. If you compare, for example, and also the presence of higher education institutions seems to be a key factor.
And indeed, events like this. Any last question just before we head off? Yes, sir, the red tie.
George Latham from Web Asset Management. I was interested in your thoughts about one of the other potential large changes, which is about how we receive our energy supply, in that the institutional lock-in, I suppose, is to have large centralised energy supply, and we've heard from Desertec earlier on this evening, but it's felt over the last 10 years or so as if there's a move towards more decentralised energy supply. Is that another change that you see?
I think that's a bit of a pastoral fantasy, personally. Certainly if you take into account the great migration that I just mentioned into the city, the notion that we will have rooftop PV and rooftop windmills that will provide our energy in a decentralized way. That's fine if you're living out in the country in Colorado or even in Somerset or something like that, but it's not going to really work for the city. So I think we are still committed to large central station forms of generation, in fact, of the sort that we heard in respect to the Desertec Foundation. And those kinds of the smart grids that will be necessary to integrate different forms of generation and to be able to ensure that you're storing intermittent sources in the grid and so on are all key factors in that. But I don't see, frankly, a move towards a highly decentralized system in which we could dispense with either large-scale generating projects or the grids that are necessary to distribute their products.
Thank you very much.
Thank you.